Okay, this is the first part A of the experiment, where we have the variac, the AC voltmeter, ammeter, sorry, and milliammeter. And in series with it, we have wire going from the ammeter to the capacitor, through the capacitor, back to the power supply. So these two things, all three of these things are actually in series. So one after the other. So we've wired that up. And we want to measure the voltage across the resistor, voltage across the capacitor, and a voltage across both of them. And you'll see shortly that they don't add up in grade school math. They add up like vectors, and we'll see this as we talk about in the presentation of the experiment. So make sure the power supply is off. Make sure that you've adjusted it to as close as you can, and that's an error there, to 100 milliamps. Okay, still, turn this off when you're making any connections or disconnections. So all you have to do is connect these leads to a bare wire, such as the bare wire leads on this resistor. Okay, so I've connected across the resistor, and let's measure the voltage across the resistor. Voltage across the resistor is 9.8 volts. And we only have two AC voltage scales, one that goes up to 200, one that goes up to 600. And so we'll use the more sensitive one. Okay, so 9.8 volts. Doing a quick calculation in your head, if this says 100 ohms, which you probably should measure carefully with an ohm meter to make sure how close to 100 it is, but these are pretty precision resistors. You can measure that by taking it out of the circuit and using your meter to measure, as you do with any resistor. But it has to be out of the circuit when you do that. So I would double check that and use whatever your meter says, which is going to be more accurate than 100. So if we have 9.8 volts is equal to 100 ohms times 0.1 amps, that sounds about right. So if that's exactly 100, that's exactly 0.1. This should be exactly 10. So that sounds reasonable. Okay, so there's 9.8 volts drop across the 100 ohm resistor with 1/10 of an amp going through it. So again, shut this off. Move one of these leads. Now there's pluses and minuses, and red and black leads and so forth, but in AC the current goes both ways, and so there's no plus, there's no minus, it's plus and minus. So ignore these plus and minuses here, and don't worry about how you hook up the leads, which one goes where, because for AC it doesn't matter. Okay, so we'll hook this lead. This lead here is connected to this terminal on the capacitor, so we'll just leave it alone. We'll connect this lead over here to some bare metal part for the capacitor. So now we're measuring the voltage across the capacitor, 100 milliamps. So the voltage across the capacitor is 22.5 or 6, 22.6 volts. All right. Now we need to measure the voltage across. By the way, the only thing that's really dangerous in the circuit is this capacitor, and as long as it's connected to the circuit, it automatically discharges when you turn off the power supply. But if a wire comes off for some reason, breaks, I don't see it happening, then you have a little bit of a problem. So we need to, actually should have left that on. Now we need to go from, and again, use the one-hand rule, just hook things up with one hand. So I'm going to move this back over to the other side, because now I'm measuring the voltage across from here to here, which is across the resistor and the capacitor. And let's see what we get. 24.8 or 9, you call it. Okay, so that was 22 volts. The total is 24 volts. That was 10 volts. Clearly, the math doesn't add up, but it does add up if you treat these as phasors, as vectors. And we talked about that in the analysis. Okay, so there's your data. do that at 100 milliamps, do it at 150 milliamps. There's an error in setting this. You have to figure that out. Okay, we have the voltage across everything at 150 milliamps. It should be no surprise that that's 50% higher than the voltage across the circuit with 100 milliamps going through it. So anyway, take these measurements and then work backwards, measurement across the capacitor, measurement across the resistor. Again, don't forget to turn this off before making any connections or disconnecting anything. Okay, that's part one, or part A. Now, this is part B, where we put the resistor and the inductor in series with the ammeter. But before you do that, we should measure the resistance of this inductor. Now, as you saw in the discussion part of this, the theory part of this, this inductor has about 3,000 turns of very fine copper wire. This is the one we made ourselves. And that copper wire, even though it's copper, has a lot of resistance. In fact, let's check the resistance of the copper wire. Okay, I'm going to set this on the 200 scale, because I happen to know it's less than 200, and measure the resistance using the battery here. Okay, so the resistance of this inductor is 106.1 ohms, roughly 100 ohms, about the same as the resistance of the resistor. So this inductor has a lot of resistance because it's 3,000 turns of very fine copper wire. All the other inductors maybe have a cover on them, but they are about the same. And so this is not a pure inductor, unlike the capacitor, which is simply a capacitor. Has no resistance, has no inductance. It's not current doesn't go through it. It's not made up of any kind of coil of wire, and so it has neither of those, but it has capacitance. So it's a pure capacitor. Part A was to show that if you treat that capacitor as a pure capacitor with an experimental error, it is a pure capacitor. So, all right, so 106 ohms, fine. So we put this back in the circuit. And we want to measure the voltage across the resistor and the inductor at 100 and also 150 milliamps, just like in part A. So let's, of course, I think we know the answer to the question, what is the voltage across the resistor when the current's 100 milliamps? And I haven't adjusted the meter very carefully. The last time we looked at it was 9.8. It's 9.6 here, but again, I haven't set that very carefully at 100. Let me do a little bit better job of that. There. No surprise. With 0.1 amps, with this resistor, whatever it is, we should measure the resistance value of the resistor, by the way, just like we did for the inductor before we continue with the circuit. To take it out of the circuit, you measure it with the multimeter, with the battery that's in the meter. So again, it's 9.8 volts. Again, no surprise. Let's go and measure the voltage across the inductor. This wire is the same. The connection here is the same as the connection there. So all I have to do is put a connection here. Okay, so we're measuring the voltage just across the inductor. Again, this wire is really connected here. This is a zero resistance hookup wire. So the voltage across the inductor is 11.5. Okay, so that's 11.5 volts. That's voltage due to some resistance and some inductance. So that's what we have to figure out. What is the angle that we're going to plot our voltage across the inductor in our diagram, in our voltage phasor diagram. Okay, so 11.5 volts, 11.5 volts. Let's go and leave that there and put this over here again. That's the voltage across both the inductor and the resistor. And the answer there is 21.3 volts. Do this for 100 milliamps, do this for 150 milliamps again. We will take this data and process it. So I think the main thing you need to do is take these data, which is done very quickly and easily without any big problems except setting the meter up, and then spend the next hour before you leave doing the analysis because it's a vector addition problem. That's what it is. Okay, so we got the data for this. We can calculate, the goal of the game here is to calculate the phase angle at which to draw the voltage across the inductor, because the inductor's got some resistance and it's got some inductance. And that whatever that angle is, that's the angle we're going to use for part C. And part C is putting the capacitor back in and measuring the voltage across the resistor, the capacitor, and the inductor, and across all three of them, and producing an impedance diagram with the angle that you figured out for part B from the inductor. So let's put that in. Okay, we have everything in series then. Through the inductor, through the capacitor, through the resistor. The order doesn't make any difference. Just hook them up whatever way they are easiest to hook up in terms of the wire leads. So we're ready to go for part C, measure the voltage. First of all, we need to set the current. Because it has more impedance, the current was lower. So I'm setting that at 100 milliamps. I'm not going to measure this. You should measure it just to make sure that you also get 9.8 again. When this is 100 milliamps, that should be 9.8 or whatever it is with your particular resistor. Measure the voltage across the inductor, across the capacitor, the inductor. Again, you should get the same answer as you did last time for the capacitor, because it's a pure capacitor with the same current and the same capacitance. We should get the same answer. So let's see. I think we got 22.6 last time. We got 22.7 or 8 here this time. Again, make sure that's set it exactly. It seems to be a little bit on the high side. Make sure that's exactly 100 milliamps. So 22.7, I think, just like last time. And measure the voltage across the inductor. And again, you should see that, as you might expect, you get the same voltage across the inductor with the same current through it, but it's the phase angle that's the issue here. So again, you need to draw an impedance diagram, which we talked about in the theory part of the lab, to figure out whether you get the same answer for the total voltage. Let's see, the total voltage would be across everything, which would be from here to here, right? So the total voltage across everything, all three circuit elements, is 27.5 volts at 100 milliamps. That's a little bit high. Okay, so that's your answer for V sub R plus V sub C plus V sub L drawn at their appropriate angles. 0 degrees, minus 90 degrees, and whatever that angle is you figured out in part B, it's going to be somewhere around 40 degrees, I suspect. It's different for the different inductors that we have. So that's the lab. It's pretty easy to do. Again, remember, please turn this off when you're connecting or disconnecting anything, and you'll be okay.